This is lecture 9.7, which is going to build on what you know about titrations for titrations with a weak acid and a strong base. So you'll be starting with a weak acid in the flask and adding a strong base, and this adds in the equilibrium element to what you already know about titrations. So it starts to get a little bit confusing. Make sure that you've looked at the learning targets and completed them first, and that you have a little bit of an outline there. And then if you need to, as you're watching through my stuff, stop the video to finish the outline. Here goes. All right, so notice that this titration curve looks a little bit different from the titration curves that you saw when it was a strong titration. So I want to definitely draw some attention to the ideas of this curve being what you saw before as a strong acid, strong base curve, right? And now we have a weak acid, strong base. So there are several things that are a little bit different. Notice that the pH is higher a little bit to begin with. So if we had the same molarity of a strong acid or a weak acid, the weak acid would have a little bit higher molarity because it's not 100% ionization. And of course that is determined both by percent ionization from the K as well as the initial molarity. All right, so the molarity of the H3O plus is determined by both of those, and the pH will be just a little bit higher. Also notice that this rises kind of quickly, but then levels off a lot. And so you see an initial quick increase because you actually have some conjugate base formed instead of using it all up and forming like only the base alone, right? Or in a strong acid, strong base, you're forming only water. So initially, the pH is rising a little bit more quickly because you have the conjugate base formed, but then it levels off, and we call anything from when there's any of the conjugate formed until we get to the equivalence point, up until the equivalence point, right before that, is technically all of this from here to there is a buffer. All right, it's not a very good buffer in the beginning, and it's not a very good buffer toward the end of that, but technically you have both conjugates in solution, this and this in solution, technically at any point between there, okay? And this is a big important difference because in a strong acid, strong base titration, in the beginning, all you have is your remaining strong acid or water that you formed, okay? So this is definitely a difference. And then the equivalence point, notice, is high. It's above 7. That's because at the equivalence point here, what we have left is only the conjugate base in water, right? So this is definitely a basic pH. So you have to picture that at equivalence, the only thing there is the conjugate base that's creating a pH, that both of these are gone. So it's a higher pH than 7 at equivalence if you have a strong base titrating into a weak acid. And then from there on, it looks very similar because now you have excess OH minus. So you treat it the same way as you did in a strong titration when you had the excess OH minus at the end. So just definitely keep track of some of these differences as you're going. I do also want to show you, I know I asked you to put some information about a polyprotic acid in your learning targets. So this is an example that would show you that you have two separate equivalence points here. Notice that the second one is actually not very distinct, that it would be very difficult to find the vertical region in there, and that's because you have two equilibrium scenarios going on and a lot of common ion. But definitely if you see two curves in that, notice how this is one kind of vertical spot. If you see two places where this curve becomes slightly more vertical, then you know that you have diprotic acid, and if it had 3 little spots like that, each one would get progressively harder to find the vertical, but they should be those little vertical burps kind of thing in there, and then at that point you know that you have another hydrogen equivalence point. So I'm a firm believer that you won't have to calculate titrations using polyprotic acids, but that you might be required to talk about how there could be 2 equivalence points or 3 for like phosphoric acid, etc. And just a reminder that if you're asked to calculate the pH of a weak polyprotic acid only, not in titration, but just alone the weak acid, then you're really only going to worry about the Ka of the initial ionization, not of all those others. So that's just a quick reminder. All right, let's do some calculations. So I want to titrate with you a weak acid titrated with a strong base. And as we do that, I want you to focus on what's in the flask, just like you did when you were doing a strong titration. So again, you should do a reference point. If you need to stop the video here so that you can write stuff, you may want to do that. And then remember that only before you begin, you have only a weak acid. So this is ice and weak acid molarity. This is the same as if you had only a weak acid given to you. What's the pH of hydrofluoric acid? So it's the same exact idea before you've started to titrate. After you begin, then you're going to find moles of the weak acid in the flask and moles of OH minus added, and you're going to set up your BCA chart and put those in. The biggest difference now is that you will be creating a buffer, or maybe as you're looking at this, you're going to use up some of the weak acid and not all of it. You're going to use up all of the strong base, and you're going to form some of the conjugate base. So for the rest of this, you have to picture what's happening. If the strong base is the limiting reactant, then you have a buffer. You have your weak acid and your conjugate base in the flask, and you're going to use the moles of both because you don't need molarity if you're using Henderson-Hasselbalch, and it's faster to use moles, and use Henderson-Hasselbalch to find the pH. Okay? If you are at equivalence and neither the weak acid or the strong base is left, then only the conjugate base is in the flask. So now you need to find the pH of a weak base. So to do that, you need molarity. You'll have to divide the moles by volume and then write your weak base dissociation, ice it. Remember that X in a weak base is OH minus, and then you'll find POH and pH. So you can already see this is more complicated than it was for strong. And then finally, just like in strong, if your, I'm going to talk about something else in a second, but if your weak acid is your limiting and your strong base is excess, then you also will have conjugate base present, but you can ignore it because the extra ionization from it will be beyond your significant figures. So you're going to calculate your new total volume and divide moles by total volume to find molarity. Remember, it will be molarity of OH, then POH and pH. So that's very much like what you do at the same point in a strong titration. So the only thing that changes is beforehand. And now I want to talk about something really cool that's special here, and that would be is if you are exactly at halfway to equivalence, pH equals pKa. And this would be because you've put in exactly half as many moles of your strong as you had of your weak. And so you have half of the weak left and the same exact amount of conjugate base formed. So they're in equal concentrations. And the numerator and the denominator in Henderson-Hasselbalch will be equal. So your pH would equal pKa. This is a great trick for them to put on the multiple choice. So I'm a big fan that you remember this. Otherwise, you can always set it up and prove it. But if it's multiple choice, it's really fast. If they go, you know you're halfway to equivalence, what's the pH? As long as you have a Ka, you can do the negative log in your head and come up with a pH. Okay? All right, so let's do some. So this example walks you through all these different scenarios, and I'm going to set it up the same way as I would have before, where before I begin, I'm going to find my moles of weak acid in the flask. And so moles of benzoic acid will be the volume times the molarity, so 0.03000 liters times the molarity of 0.100 molar, gives me 0.00, I've got an extra decimal, so 0.003, and I still have 4 significant figures, so I got to keep adding all those zeros. All right, so this is moles of my benzoic acid in the flask at the start of every single one of these. The other thing that I'm going to do is find the volume of NaOH to reach equivalence, just so that I have that benchmark. All right, and I showed you in class, I think, of how to use VM. So this would be number of hydrogen times volume times molarity of the acid, and volume times molarity of the base times the number of OH minuses. Okay, so I'm going to set this up with the volume. Now it has to be in liters, so I'm going to do, again, actually it could be in milliliters, but I might just kind of do it always the same for you. So 0.03000 liters, 1 hydrogen in benzoic acid. You're always doing 1 hydrogen in your acids, whether they're polyprotic or not. And the molarity was 0.1 molar equals the volume of the base, which is what I'm looking for, the molarity, which is 0.15 molar, and sodium hydroxide has 1 OH minus. So the volume of the base needed to get to equivalence will be 20 milliliters or 0.02000 liters because I have 4 sig figs. All right, so this would be at equivalence. So there's my benchmark. All right, now I can actually start working the problem. So I'm going to do these in different colors so it's color coded for you. The initial pH before the titration begins means it's only benzoic acid in the flask. So because A is a weak acid, then you're going to write the weak acid dissociation equation. So this would be benzoic acid plus water gives you H3O plus the benzoate ion, and I'm going to do ice because it's a weak acid. My initial molarity, remember ice needs to be molarity, my initial molarity was given to me at 0.100 molar. Neither of those are in the flask in the beginning. So this is minus x, and I get 0.1 minus x. And I'm going to set this equal to Ka, which is 6.3 times 10 to the negative fifth, equals x squared over 0.1 minus x. Get rid of the x. When I solve for x, I get x equals 0.0025098, a bunch of numbers. And that, I have to remember, is the hydronium. Okay, so at that point then, now I can take the negative log of that to find pH. And that would be 2.600329. I have 2 significant figures from my Ka. So pH equals 2.60. Remember, those are my sig figs. Okay, so that was the beginning before I started. Now it's going to get a little harder. So now I'm going to add the base, and I'm going to add 12 milliliters of the base. So this is a one-way equation, and I'm going to write my benzoic acid that was in my flask plus the OH minus. It's one way because that's strong, and that's going to give me water plus the benzoate ion because the hydrogen will transfer this way. I need to know BCA so that I can figure out what's left in my flask. I already figured out that I started with 0.00300 moles of benzoate, remember, or a benzoic acid. This has got to be in moles. And I need to figure out how many moles of OH minus I've added. So I'm going to do 12 milliliters or 0.01200 liters times its molarity. So this is going to be finding moles of OH minus times its molarity at 0.15 molar. Tells me that I have 0.0018000, oops, too many O's, moles of OH minus. So that's going to go here. And I don't have any of this, or I don't care about the water, and I don't have any benzoate ions because I'm starting from scratch. So now this is the limiting reactant, so minus 0.001800, minus 0.001800. This is 0, but I have to remember to add it to the other side. This is now 0.001800, and this is going to be 0.003 minus that, which is 0.001200. Notice that what I have in my flask is benzoate, or the benzoic acid and the benzoate ion. This is a buffer. So I'm going to do Henderson-Hasselbalch, which would be pH equals the negative log of Ka, so 6.3 times 10 to the negative fifth, plus the log of the conjugate base, in this case the benzoate ion, 0.001800, and I can do this in moles because it's a ratio, so this is quick. 0.001200 for the acid. Remember that this has to be the conjugate base over the weak acid. Okay, and I plug that into my calculator, and I find that pH equals 4.37675, blah, blah, blah. I have 2 sig figs from the Ka, so this will be 4.38. All right, so we keep going. That was when it's a buffer, and it will be the same as that all the way up until just before the equivalence point. Now, at the equivalence point, I have put in exactly the same amount of sodium hydroxide as I had mole-wise of benzoic acid. So again, this is a one-way. I'm going to write my same equation. H benzoic plus OH minus. One way because it's a strong gives me H2O plus Benz minus. BCA, I had 0.003 moles of that. I'm going to add the exact same amount because that's at equivalence, and I've got 0 of this. Now notice they're both limiting, so minus 0.003000 minus 0.00300 plus 0.00300. These are both 0, and what I have is 0.00300 moles of Benz minus, which is a weak base. So this means I need molarity and ice. So I have to take the concentration of Benz minus is going to be moles per liter. So this would be moles of 0.00300 moles left. That was what was left here, right? Divided by the new volume. So I started with, come back up to the question, I started with 30 milliliters and I've added, we decided at equivalence, we had added 20 more. Okay, so this is going to be 0.03000 liters plus 0.020000 liters. And I find out that the molarity of the benzoate ion, which is my weak base, is 0.06. I have, let me double check this. Yep, I think I have that many 4 sig figs still. Okay, so now I'm going to substitute this in, and this is my molarity, and I need to write the weak-based ionization equation. So I need to put this in water. This, remember, is the weak base, so this is going to form H-benz and leave behind the OH minus. And to find the pH of a weak base, I need ice and molarity. So this will be 0.06000. The water I don't care about. We're going to see what it does. Minus x plus x plus x. 0.06000 minus x, x, and x. And now I need to set it equal to KB, which will be x squared over 0.06000 minus x. Cross off the x. I have to find KB, but I don't really need to know the number, so I'm going to do 1 times 10 to the negative 14th divided by Ka, which was 6.3 times 10 to the negative 5th. And I'm going to cross multiply and solve for x. I do have to remember that now x is OH minus. That's really important. And I found that x equals 3.0861 times 10 to the negative 6th. I'm going to do POH equals the negative log of that, which comes out to 5.51059 more numbers. pH equals 14 minus that. So that comes out to 8.48940 more numbers. And I actually still only have 2 sig figs from the Ka that I put in there. So this will be 8.49 as the pH. All right. Whew. You getting tired of this yet? All right, let's see what happens. After equivalence, we're going to add 22 milliliters. Notice this is after equivalence, which was 20 milliliters. So after equivalence, I have to do the same things. So after equivalence, sorry, this is D. After equivalence, 22 milliliters is 0.02200 liters of 0.15 molar OH minus. And that gives me 0.003300 moles of OH minus. I'm going to do the same thing, Benz minus plus OH minus. I always pretend I'm starting over one way. Gives me water plus H Benz. Nope, sorry, I started that wrong. This was, let me start all over. I'm sorry, I'm titrating my acid, H benzoic acid plus OH minus. This goes this way, gives me water plus Benz minus. Sorry, did not mean to mess you up. I'm still titrating, so this is a one-way equation between the acid that was in my flask and the OH minus that I've added. This is BCA. This is still 0.003000 because that's how many moles were in my flask of benzoic acid. I've added 0.003300 moles of hydroxide. So now the benzoic acid is limiting, so it's minus 0.003000 minus 0.003000 gives me 0 and 0.000300. And over here, plus 0.003000 gives me plus 0.003000. Now, what I need to notice is that what's in my flask is the OH minus, which is excess, and Benz minus, which is a weak base. So because it's a weak base and you have strong base left, now you can ignore your weak base. And this would be because any ionization that occurs is going to be hampered by the OH minus already in solution. And so it will be beyond our significant figures. So this means I have strong base left. So I need molarity then of the OH minus. And then I'm just going to do the negative log of that and subtract from 14. So molarity will be, OH minus concentration will be 0.000300 moles divided by my new volume, which was the 30 milliliters initially in the flask, plus 22 more, so 0.02200 liters. And I find that the molarity of the OH minus is 0.0057692 molar OH minus. So POH will be the negative log of that excess OH minus, which is going to be 11.7, oops, sorry, I jumped ahead in my work. Will not be 11, will be 2.2388882 more numbers. pH will be 14 minus that, which will then be 11.76111179. And I have how many significant figures? I think I have 3 significant figures for my number of moles that are left. So this will be 11.761 as my pH at this point. All right, only one more question. I asked you here at what volume of adding sodium hydroxide will pH equal pKa. So remember that this occurs at halfway to equivalence because you will have added half as many moles of hydroxide as you had of your weak acid. So since my equivalence volume is 20 milliliters, halfway of that is 10. So at this point, my answer to this would be at 10.00 milliliters or 0.01000 liters. I will have pH equal to pKa, and I could solve for that if I want to. But remember that that's because in Henderson-Hasselbalch, what I'm putting in here is this ratio would be equal at halfway to equivalence. Okay, so if you have questions, make sure you bring them with you to class, and I will see you.